Hey, this is Mr. Schultz. We're going to do a short video here. The video from today crashed on me, so we did not get a chance to upload that because it crashed. So just going to make a little mini lesson here. We're going to be talking about shifted geometric sequences, which we've actually already been doing these. And the big new piece is going to be find a long-run value. So let's first start with the shifted geometric sequence. So geometric sequence, we should recognize that. That's just where we're multiplying. And then what's the other type of sequence that we have there? The arithmetic. That's when we're doing the addition and subtraction there. And then what shifted means inside of this is it's just what we've been doing with our loans and investments. Loans and investments. We've just been having the multiplication from the geometric, but then we've also been having outside of it, outside of the parentheses, we've been having an addition or subtraction sign there of some other piece of money that, in our case, it's been money that we've been putting in there. So shifted geometric just has the geometric, the multiplication, but then it's also got your addition and subtraction piece with it there too. So we definitely have been doing these already. I'll show you another example of that. So the big thing for today, though, is to find the long-run value. So a long-run value, sometimes referred to as a limit. That's the word that you'll be seeing a lot when you go further down the line and be going into calculus and different pieces like that. So it's basically saying a sequence, it's a value that a sequence or function approaches but doesn't actually touch. So it's a lot like an asymptote. So if this is our long-run value here, this thing is getting closer and closer and closer, but it's never actually going to touch that that value right there. So so graphically, just to take a second and look at that, what you're looking at is just something that is leveling off. So far, everything that we've been doing, we've been getting stuff that's been growing exponentially or that we've been paying back exponentially, so it'd be something like that, but then we're stopping there once we get to zero because we're paying it back. So just stuff that grows without bound. Now we're going to be looking at stuff like this, where it is just continuing to just to basically flatline and stop doing anything. So as you go farther and farther out, this thing is just going to just keep sitting right there, just flatline. And it's technically getting closer and closer and closer to a value, but it's just staying flatlined. So do you get this? So when I get way down this line here, let's say that this point here, my u, basically that this point is basically the same thing as that point right there. It'd be like saying if I had $1 billion, and then you said to me, well, I've got $1 billion and 2. Both of us would look at each other and basically say, yeah, this is more or less, these are the same thing. That's basically the same thing in the long run. The $2 is so minimal of difference that it's basically the same thing. That's the same concept that we're looking at right here with this. We're just saying that u sub n minus 1 and u of n they're basically the same value because they're so close in the long run. So what that means that we can do is we can take an example like this guy, and since u of n and u of n sub 1, or u of n minus 1, are basically the same value in the long run, we're just going to replace those with some unknown value, and we're just going to call that unknown value x. And then from here, it's just a normal algebraic equation. So we're saying that x is equal to 0.5x plus 16. And then we're just solving. So we're going to subtract 0.5x, subtract 0.5x, and this is 1x, and we just never write the 1 on there because it doesn't do anything, but this is actually 1x. So subtracting 0.5x, end up with positive 0.5x. These cancel, left with 16, dividing by 0.5 on both sides. X is going to end up being the same thing as 16 over 1/2. And then what happens when you get a fraction over a fraction? You flip the fraction, and then you multiply it. So this would be the same thing as saying 16 multiplied by 2. Because we're just flipping this fraction right here making it 2 over 1, and then we're multiplying it by the 16. Our x, or our long run value, ends up being 32. So in this guy, the long run value is 32. But don't take my word for it. Let's punch that into our calculator. All right, so we've punched that into our calculator here, and we're just going to take and figure out what is our long run value just by seeing a list of the table values. So looking at the table here, you can see how this number here is continuing to go up, but then it starts to kind of level off here. So basically, if you're going to make this look like a graph, you know, it's going up, and then it's starting to level off here, and it looks like it's leveling off right around 32. And so if you take a look at that here, you can see that it's getting closer and closer and closer to 32. Eventually, your calculator will tell you that the value is 32, but it's just because it runs out of decimal places to put 9s in, so it just rounds. So that's a time that you have to be a little bit smarter than your calculator. So why don't you go and take a stab at this second one here, then we'll do that in a second. I'll pause the video. All right, so now that you got a second to look at that, pretty simple. We're just replacing the u of n minus 1 with an x, and then we're just solving the equation algebraically. It's 1 minus 0.25, with 0.75x plus 20, and that's all equal to x. Subtracting our 0.75 from both sides, subtracting 0.75, going to end up with positive 0.25x is equal to 20. And then with that 0.25x equal to 20, divide by 0.25, divide by 0.25, we've got x is equal to 20 over 1/4. Same thing, we're flipping and multiplying, so x is equal to 80. So our long run value in this situation would be 80. That's really all that we're doing. We're just replacing these with x to find the long run value. The key piece is, when do we know that it's going to be a long run value? A really good indicator is if you've got a negative sign here. It doesn't mean that it's going to be a long run value, but you do need to have some sort of a decay that is causing this thing to be able to go to a long run value. So like if we look at some of the ones we've been doing in the past couple of days, we can see that these all have pluses here. This would be 1 plus 0.23, so that's got the plus there. It's got the plus here. So all these things are growing, and as you can see by the graph here, it just keeps growing. It's not approaching a value like if you were to do something like that. So since this is not approaching a value, there is no long run value for any of these, because we can just take a look at our graphs and see that they are increasing or decreasing without end. They just keep going on and on and on. So be careful and watch for that. If you see something with a decay, that's a hint that you might be looking at a long run value. So take a look at that. Our next piece here is going to be another example of a long run value. So let's say you had a can of pop that's 25 grams of caffeine. Your kidneys will filter out that caffeine through your bloodstream at a rate of 3%. So it's taking out 3% of the caffeine. Write a recursive formula to represent the situation and find the long run value. Why don't you take a second and take a look at that. All right, so we're taking a look at the recursive formula for this. So u of n is equal to u of n minus 1. And then we are multiplying that by 1 minus 0.03. And that's it. That's all of our recursive formula. You do, in theory, to make that recursive formula, you would need this as well. But all of this stuff for finding long run values, all this stuff doesn't really matter. We don't need to look at that. So to find the long run value from here, same thing. Just putting x's in and solving. So x is equal to, this is equal to 0.97, so 0.97x. And we're subtracting 0.97x, subtracting 0.97x. You end up with 0.03x is equal to, and 0.97x minus 0.97x is equal to 0. Dividing by 0.03, x is equal to 0, because 0 divided by anything is always going to be 0. So in this case, our long run value is 0. It's just getting smaller and smaller. which makes sense because if you take 3% of something constantly, it's never going to reach 0. It's just going to keep getting closer and closer and closer towards 0. So that's the shortened video of what we did in class. It's just basically replacing those u sub n's and u sub n minus 1 with x, and then solving for x to find your long-run value. But just be careful and watch for the times that it could be a long-run value or that it might not be. Because, for example, in our last one here, if we replace these with an x and found the long-run value there, we could find a value, but it wouldn't be a long-run value because the equation keeps growing and growing and growing. So just be careful and watch for that there. And that should be everything we have for you. Thanks.